Okay, so in this video, I'm going to go through section 10.5, which is title testing a claim about a population mean. So in this video, we're going to go through the following example. The daily temperatures in fall and winter months in Virginia have a mean of 62 degrees Fahrenheit. And so the fact that we're talking about a mean, this is their assumption. So this is our null hypothesis that the mean, or mu, is 62 degrees Fahrenheit. That means that if we have anything that uses the variable mu naught, we're going to use 62 degrees as that value. A meteorologist in Southwest Virginia believes the mean temperature is colder in this area. So they believe something, and so that means that's going to be an indicator of our alternative hypothesis. The meteorologist takes a random sample of 30 daily temperatures from the fall and winter months over the last 5 years in Southwest Virginia. The mean temperature for the sample is 59 degrees Fahrenheit with a standard deviation of 6.21 degrees Fahrenheit. Do the data provide convincing evidence at the alpha equals 5% level that the mean temperature in fall and winter months in Southwest Virginia is less than 62 degrees Fahrenheit? So colder means less than. So our alternative hypothesis is what the meteorologist believes, that the actual mean is really less than 62 degrees Fahrenheit. And remember that mu represents the daily temperature in fall and winter. In Virginia. So then what we want to do is identify our plan for the test. So given the same example, in order to see what kind of test we're going to use, we want to think about first, how many samples are in the problem? And then second, what type of statistic are we looking at? So if I'm thinking about this for the sample, that means that we only have one sample. And then if we're looking at our statistic, we're talking about a mean. So remember that if it's mean, we're doing a t-test. If it's a proportion, we're doing a z-test. So that means that we are doing a one sample t-test for this. So we have to check our conditions for a one sample t-test. So we want to check three things. We're checking that it was a random sample. And so if we look at this for random, let's see. They get a random sample. So we are random. That one's good. And then we want to check, does it meet the 10% requirement? So it's 5 years worth of fall and winter months, right? So if I think about that, that's roughly half the year, right? So if I have 365 days in a year, and let's just say we have 150 days that we're choosing from, times 5, 30 divided by that number is going to be less than 10%. So since I have a large population of 5 years worth of days, that means that 30 is going to be a less than 10% of that value. That 30 is also our value for the sample size. So that's our N. And so with that, that helps us with the normal or large sample. So remember that it has to tell me either the data is normally distributed, which it does not, or my sample needs to be greater than or equal to 30, which is what is met in this condition. So we have met all three conditions in order to perform a one sample t-test. So using that, we can calculate our values. So remember that within this problem, we talked about this 62 degrees Fahrenheit. That's going to be the value for mu naught. Okay, so 62 is the value for mu naught, which means that 59 degrees is the amount from our sample. So that's going to be the mean of the sample, or X bar. So remember, X bar is the mean of a sample. Mu is the mean of the population. And it's mu naught because we're assuming it's the mean. We don't know for sure. So X bar is 59, and then the standard deviation of our sample is S sub X. So the standard deviation of our sample is 6.21. And then we know from the previous one that our sample size is 30. So N here is 30. And then with that, we have everything we need to calculate the value for T. So if we look at this formula, we want to figure out what the answer is for T. So let's plug everything in. So we're going to do X bar minus mu naught divided by standard deviation over the square root of N, which was 30. So that means that we're going to take 59 and we're going to subtract 62 and then divide that by 6.21 over that square root of 30. So if we calculate that, we get a T value of negative 2.64. Okay, so we have a T value of negative 2.64. So I'm going to go to the next slide and look at the T chart. So we got a test statistic of T equals negative 2.64. So remember that with the T's, I only have positive values and I'm looking inside this area for that value. So I want to look for two things. One of them is the degree of freedom. Remember that that is N minus 1. In this situation, our sample size was 30. So that means that our degree of freedom is 29. Remember that if that 29 was not on the T chart, we would round down. In this case, though, 29 is on the chart. And so that means that when we're looking for our T to identify the proportion, or sorry, the p-value, we can use that line. So we're going to use the line of 29 in order to look for the p-value. So we're looking at these numbers for our T, or as close to our T as we can get to find that value. Okay, so what we're looking for now is this number, or as close as we can. Notice that it's negative, so this chart is only positive, so we're looking for as close to positive 2.64 as we can get. So if I'm looking for positive 2.64, I see that that is between these two numbers. It's between 2.462 and 2.756. So my T value is here in between those two numbers. That means that our P value is somewhere between these two numbers. So our P value is greater than 0.005, but less than 0.01. So it's somewhere between 1% and 0.5% for this problem. Okay, so our answers are that our test statistic T is negative 2.64, and our p-value is somewhere between 0.005 or 0.5% and 0.01 or 1%. So what we want to do is use that p-value to identify a conclusion. So I'm just going to write down what we had for our p-value. So remember that our p-value was between 0.005 and 0.01. So it was between 0.5% and 1%. If I'm comparing that to the alpha equals 0.05 level, so I've got this and I want to compare to alpha, which is 0.05. If I really just look at our first value, our largest value, this one compared to this one, notice that it is less than. So I know that my p-value is less than alpha. So remember that when your p-value is less than alpha, that means that we are going to reject the null hypothesis, which means that there is convincing evidence. That the true mean temperature is less than 62 degrees Fahrenheit. Okay, so using a one sample t-test, we found a value for t that allowed us to determine a p-value, which was less than our significance level alpha, which means that we're rejecting our null hypothesis, that there is convincing evidence that the true mean temperature in Virginia during the winter months is less than 62 degrees Fahrenheit. The last thing that this section focuses on is type 1 and type 2 errors. So a type 1 error is when you reject the null hypothesis, but it's actually true. So you have convincing evidence that the alternative is true when it's not. Okay, so what this means is that for this example, if I have a type 1 error, then based on the sample mean, the meteorologists would conclude that the mean temperature in fall and winter months in Virginia, they're rejecting the null, so it is less than 62 degrees Fahrenheit. But the true mean temperature is actually not less than 62 degrees Fahrenheit. So that's a type 1 error. A type 1 error is that I reject the null hypothesis when I shouldn't have. Okay. A type 2 error is the opposite. I fail to reject the null hypothesis when I shouldn't have. So based on the sample mean, the meteorologist concludes that a mean temperature in fall and winter months in Virginia is not less than 62 degrees Fahrenheit. So I'm not rejecting my null. I'm saying that I don't have evidence for this when the true mean of temperature is actually less than 62 degrees Fahrenheit. Okay, so when it's a type 1 error, I'm rejecting the null when I shouldn't have. And when it's a type 2 error, I'm not rejecting the null when I should have.